Awesome. Hi, everyone. Thank you for coming to another series of the ISI NL seminar. Today, we have Tanmay Parekh, third-year PhD student from UCLA, who is advised by Professor Nanyan Peng and Kai-Wei Chang. He's done his master's at LTI, Language Technology Institute at CMU. And before that, he used to be at IIT Bombay, where he did his undergrad. His main research actually focuses on improving the utilization and generalizability of large language models for applications, particularly in information extraction across various languages and domains. Today, we have him giving us a talk on something very interesting with epidemic prediction, I think very timely. So without further ado, let's welcome Tanmay.
Thank you, Justin, and thank you everyone for hosting me. It's a privilege to just give a talk here as well. This still might be one of my early talks, so just interrupt me with anything. I'll be happy to answer questions about it. Cool. Okay. Yeah. So today I'll be talking about my topic on event extraction for epidemic prediction. This talk will be kind of interchanging between technical stuff as an NLP practitioners, but also application-specific things, which will be related more to epidemic prediction. So I'll try to switch between both, and that will be just the way we'll go about the talk. Cool. So I'll just try to jump into the title itself, give a quick 10-minute intro of what this talk will be about, and then we'll jump into more specific stuff. So I want to first describe what we mean by an event. There are a bunch of definitions, but a very simple, more lame terms is like something that happens or some deeper semantic action. So for us, we can think about like stuff like accident, birth, leadership, merger, infection, bunch of things like this as event. It's kind of a semantic action which we as humans define as something happening. And that's the definition of event that will follow for this talk. Next, we have the term of event extraction. So this is like a specifically designed task in NLP itself. And a more concrete definition for this would be extracting structured information about events from natural language text. And mainly we divide it into two kinds of tasks. We call it event detection and event argument extraction. So just a quick brief intro about both of them. Event detection is concerned mostly with identifying what kind of events are being talked about in the text. Event argument extraction is extracting more information about who's participating in the event, what is their role with respect to this particular event, and more deeper information about the event itself. So those are just the quick distinctions about the two subtasks of event extraction. So let's just maybe go through an example and we'll know more about it. So I have a sentence here: King Hammurabi led Babylon to victory. So what I can say is the word led indicates that there's a leadership event going around here. And just identifying that there's a word led and this is calling as a leadership event is just a task of event detection. But once we know that there's a leadership event, we can also identify that King Hammurabi is the leader here, and we have Babylon, which is the governed entity in this case. And identifying these particular participants with respect to this event is the task of event argument extraction, right? And I just want to make a quick note here without going into it, without spending a lot of time, but just how these tasks are evaluated. We use F1 scores for both of them for just identifying and classifying it into a specific class. And I called it Tri-C and Arc-C. So these will be the two terms I'll use across my presentation for any kind of evaluation that I'm doing. So Tri-C is the F1 score for event detection. Arc-C is the F1 score for event argument extraction. Yeah.
I'm not an NLP person.
Yeah.
It's a really dumb question to ask.
Sure.
When you're talking about event argument extraction, is it that King Hammurabi is the thing that is some lead as you're extracting that is the thing we're talking about, or is it extracting that semantically that is the leader, or both?
Sort of both. So we extract that King Hammurabi is a participant in this event, and we also tag it as the leader of. Okay. So yeah, I think in the next slide I'll talk about it where I'm saying that
So some would argue that semantically maybe the victory is the more salient event in the sentence, even though it might be expressed, inside prepositional phrase. whereas, semantically, maybe the leading is secondary and the winning part is primary. You make an effort to.
So it honestly, as the task itself, it is dependent on the kind of events that of interest. So we do not care about primary or secondary events in the sentence. But if you want to extract information about the victory event itself, then I would also have another annotation which would mark victory as the event type, and we'll have particular participants with respect to the victory itself here. So event extraction does not care so much about what's the primary action or secondary action happening in the sentence, but given a set of events that you want to extract, it cares more about extracting any form of that event from the sentence.
You're not limiting yourself to a single event.
We are not.
This is just an example. It is not.
Yeah. This is not an exhaustive annotation of the sentence itself.
Okay.
Yeah. As we saw that we talked about leadership, leader, and event, but you can just have a bunch of these different events and participants. So all the ones in red are technically called as event types with respect to NLP, and each of the participants of the event types are called argument roles. Something I want to highlight here is you will have different kind of roles for different events. So leadership has leader and govern, but victory can have victor and defeated. Death can have a person and cause, and there can be a wide range of arguments per event type. And in general, event types and argument roles comprise of this event ontology. So this is something which is predefined. You say based on your application, you can define your event ontology, and event extraction will extract those kinds of information from the text. So that's a quick brief intro about just event extraction itself and how we go about it. And now I'm going to take a switch to the next term of epidemic prediction, which is more of what we want to do as part of this talk. So I do not have a very technical term here, but this is something which I defined it for my work, which is about saying that we want to extract any kind of information that can provide early warnings, basically, for any possible epidemic which is going to happen in the future. I just want to highlight the two terms about providing early warnings, because that's the key thing here that we're trying to optimize from a technical perspective. And for any epidemic, is we don't want to make it disease specific. If there's an unknown epidemic coming, we want to still be able to do that. So let's see an illustration of how an epidemic happens. This is just a timeline of how it would possibly happen. There's a time of inception where there are some initial cases and it's spreading at the local level. If it's just uncontrolled, it will grow exponentially, and there'll be a time when you'll call it an epidemic or a pandemic when you just have a lot of people who are infected with this particular virus. But technically, you will also have government or public service officers who do a detection phase, and once they detect that it's increasing, you'll have some control measures which will some sort of reduce the epidemic impact possibly out there. So this is a realistic scenario of how an epidemic curve will look like. The goal here, or the idea here, is the earlier we have the detection phase, the earlier you can have the stop measures in, the earlier and the smaller will be the impact of the epidemic. So this is just not an illustration which I want to give, but the red line and the green line is the difference that it all makes. And we also did see this for COVID. So this has been backed by data as well, where people said even if we had warnings 1 to 2 weeks before what we had currently, we could have had a 2x to 4x reduction in the infections and the deaths which COVID-19 had as a pandemic. So that's the impact that we can possibly do with this work. But from a technical side, what matters is trying to minimize TD, which is the time of detection. The earlier we can detect it, the greater impact that we can have. And I just want to give a quick background about what people have been doing here as well. So as NLP practitioners, we have made a lot of progress in creating these classification models for a wide range of tasks. You give it a text, you give it some classes, and we can build a specialized classification model for it. But as epidemiologists, the scenario changes a little bit. They are more concerned about practically applying it. So they applied a bunch of data, which includes social media data, news data, clinical notes, bunch of things for doing epidemic prediction. But the point is, their knowledge with respect to NLP is not so great, and they typically would use much simpler models in doing so. So the current best models were just simply keyword-based methods or just word-based classification methods for these things. And in general, they're very rudimentary in design. So we don't have specialized models here. And the second is they're very disease specific. So now we have a specialized model for COVID, which can detect COVID in the future, but the next epidemic possibly is not going to be COVID. So that model does not serve a very great purpose for the future. And second is, in order to make these disease specific models, you have to collect data. So you have to still wait for a particular time to collect that COVID data, build that model and apply it. So your TD is already delayed by quite a bit.
Basically, by that you mean you mean this specifically term that it's being fine-tuned on COVID data.
Yes. Yeah. So that's where we want to fit in. That's where we want to kind of utilize event extraction for epidemic prediction to try to solve this problem. And I was going to give you a teaser figure of what we can possibly do. So given a sentence, something like this, what we can extract through event extraction is there are some kinds of symptoms and infection events. So like I'm feeling nauseous, maybe I have COVID and something. So we can extract that there's some symptom event, there's some infection event happening here. And we can also extract some important arguments like person, symptom, disease about this specific event here itself. And the other thing I want to highlight is about the early prediction itself. So this is just an illustrative graph, what we can potentially do. So this is a graph for monkeypox infections from May 2022 to September 2022. And this is the number of infections and how it rose. This is a time when WHO issued a global warning that this is a global concern and people should take measures to stop it. This is also a time when all the other systems, the keyword-based, the word-based systems could actually give a warning that this is increasing quite a bit. And these are the times where our system that we developed as part of our work could potentially give warnings. So this is like 4 to 9 weeks before WHO issued a warning, before other systems could issue a warning, that we were able to say that there's an infection happening, have a look at it, and they can potentially help. So just a teaser figure, we'll get to this in the later part of the talk, but just to motivate and keep everyone engaged here.
Just to clarify the WHO warning, I mean, I assume though that's, maybe after they got their initial reports, they probably have to verify in the lead time there.
Yeah.
So they probably have triggers in place, which might have been significant earlier.
That's true. I do agree, but I do not have the data of when actually they would have received it. So this is the best data point I have. But us still being able to do it 4 to 9 weeks is still commendable, and I do not assume that they have it somewhere around here itself. Yeah.
Especially if the other systems are like right.
They kind of triggered right before WHO, because that's when people started talking about it much more at the global scale, and then WHO issued that warning that this is something that should be done. Cool. So yeah, that's a quick intro about what my talk would be about. Any quick questions about this until now? Yeah.
So there's this famous quote that Paul Krugman predicted 10 out of the past 6 recessions. So I mean, clearly there's a false positive risk here as well. And is that what do you feel like is more important, the false negative or the false positive?
I think I would leave that to the public policy officers to decide, and that's their job to do. For me, what's important is having a good recall. Like whenever there's an epidemic, if you can predict that the epidemic, that's a good thing. Detecting a false positive is up to them, and they can verify whether it's happening or not. But if you're missing out on an epidemic which is happening, that's the worst part, and that's the situation where we don't want to be. So I definitely see the false negative to be a much bigger thing than a false positive.
Well, so all you want to do is have a good recall, then you have a very simple outcome.
True. I mean, a good recall, but with still trying to optimize decision as well.
Hopefully you have a good answer.
Yeah. So it's really difficult to measure it here, but we'll try to show in our best way possible.
I think the approach is very valid there. I mean, even if you have a few false negatives, just to have the initial alert might kind of help you to kind of focus a little bit more on monitoring certain areas and certain keywords a little more closely.
Yeah, that makes sense. But you don't want to have people tune out your system kind of.
Yeah, I mean, there's of course there's.
I mean, there should be definitely other checks in place if you're finding finally implemented. But this is still the point being, no other system would be able to do such an early warning itself in the first place, and that's something that we bring to the table here. Yeah. Cool. So as part of this talk, I'll be talking mainly about 2 works. I just want to pitch it in a succinct way. So the first work is about how to apply, where we go on the journey of going from event extraction, which is an NLP task, to the application of epidemic prediction and what we are able to do using this. but this is typically just in English and just on a small system. So this is just an application perspective of the work. The second one is about how to practically apply it. So the point being, we have the world, epidemics can just originate anywhere in the world. And if people are talking about it, they can talk in any kind of language across the world. So we want a system of event extraction which can do this across different languages. So the second part of the talk is more technical, which is just about multilingual event extraction. We do not particularly show this for the case of epidemic prediction, but the main goal here is how do we just, as a sole NLP task of event extraction, improve the multilinguality aspect of it. So that's the second part of the work.
General question.
Yeah.
Did you focus on epidemic extraction because it's sort of a public good thing, because you're particularly interested in epidemics, or because you just happen to have a COVID-19 data set that was like the biggest, could you predict sports fandom? Could you predict, stock price, whatever else, right? You had the data for that.
I mean, the system, however we present it, should be able to do this, and you can apply it for a bunch of different applications. For me, definitely, epidemic prediction was more important because, again, a good social cause. So, that's where we focused on. But as we'll talk about it, you can definitely just cut paste things and apply it for any kind of different application that you want it to be. Yeah. Cool. Okay. So moving on, first I'll talk about my first work about how do we apply event extraction itself here. So yeah, this is the work. This is gonna appear at NACL 2024. It's about event detection from social media for epidemic prediction, and a bunch of people on this work. So just a quick overview, what we'll be focusing on. We are focusing on the social media platform here. We are focusing on tweets and in general, that's the focus area. You can definitely, again, apply it for different regimes, but in this talk, in this work, I'll just mainly be focusing on tweets. Second, we look at a bunch of diseases, primarily COVID-19, because that's the largest database that we had. But we also show that, just by training stuff on to COVID-19, you can also apply it to a bunch of diseases which are independent and very different from COVID-19, including monkeypox, Zika, and dengue. And a general flow of what this work will be about, we talk about how we created this data set of speed, that we call it. How do we do this training testing of models, how different models fare on this task, and how do we actually infer on real data and make this task more applicable to real data. Cool. So just a brief background again from a side of epidemiology itself. A lot of numbers and a lot of things here, but what I want to highlight here is typically there are a bunch of works which have worked on this direction, but most of them do not focus on social media data. Most of them focus on news, and social media has always been one step earlier than news. News captures what social media trends are, but social media is the place where you see the first trends appearing in. So that's why we focus on social media data, but most of the works do not do that. And other things are about many of his works being very disease specific and very fine grained. So a bunch of works focus on clinical data, and it's more for identifying specific terms about COVID-19 or clinical terms itself. But these things are not what people talk in social media. So in general, the takeaway is nobody has done or tried event extraction to solve this task. And we are the first ones to try to do this from an event extraction perspective. So I'll jump starting into how we do this data collection, data annotation kind of stuff. I'm going to quickly rush through it, but just stop me if any questions or doubts. We look at a bunch of past ontologies, and the major step I would say is trying to identify the social media relevance. So there are a bunch of events, there are a bunch of things which might be important and from a perspective of epidemic prediction, but people do not talk about in social media, right? I'm not going to talk about what variant of COVID and what kind of disease virus transmission rate is there for that particular thing on social media. But what I'll be talking about is, my neighbor got sick. I'm really worried. I'm having COVID. What do I do? And stuff like that. That's what people talk about on social media. So this is a step wherein we kind of filtered these events and made our ontology something which is more relevant to social media. And we did this validation through some public health experts as well. Does it make sense? Does this ontology look good? And we mainly captured these 7 events that are of interest for us. So it's about infection and spread of a disease. How does it happen at the local scale? So what are symptoms of the disease? What are some prevention and control measures? Prevention is more about, I do not want to get this disease. What do I do? Control measures is like, my community does not want to get this disease. What should we do as a community? What is the government doing as a whole to solve this problem, kind of stuff. And then we have cure and death. So like, if I want to cure, if I have COVID already, what am I doing? And death is about just like, okay, somebody passed away. So how fatal this disease is. People talk about this on social media. The next thing is about data collection. So again, like we create a base data set of tweets in general. So we use like the COVID-19 endpoint. We do a bunch of processing because they're like millions of tweets. Like they have like 15 million tweets per day that we could record for COVID itself on Twitter. So that's a lot of tweets. But we did a bunch of pre-processing, filtering. There are more details in the paper, but I'm just going to skip this for the time being. But we filter out a bunch of tweets which are more relevant for the task itself. And then we get a bunch of expert annotators, do this study to make sure that the quality of the data is good. We do a quality control where we verify the annotations again and create this data set of speed. And just again to put in, this is the first, like from a very event extraction perspective as well, this is the first data set for event extraction in the social media domain as well. So people have not really explored that in perspective as well.
Are you requiring that there be triggers when there's an event?
Right now, yes. For this task, yes.
What was the question?
I was asking, so right, an event is kind of like centered around a trigger, the word indicates event, but there can be an implied event, right? So it's like, you know, I don't know. So I'm just sorry.
So I'm going to go through some examples for the design choice and just want to highlight why our data set is different and important in different ways. So one is we are actually trying to capture actual and clear events, but not like vague events in the past. So something like stay at home, wash your hands. This is very relevant if I'm reading it from a COVID perspective, that they're trying to talk about some preventive measures and stuff, but it does not clearly mention why you want to do these actions. I could just tell you go for a run, but it has nothing to do with COVID itself here. So we do not mark or capture these events as part of our annotations.
Just stay and wash your hand, you're intelligent.
No, so this sentence would not be, if I get this sentence, I would not annotate the sentence for any kind of event here.
Because stay and wash are not part of the intelligent.
Oh, no. It's not about stay and wash at all. It's about, I don't know what these actions. It has to be related to saying that it has to avoid some disease. If you don't want to catch COVID, then do this. And then I would try to mark this. But this is just like a action, right? So like, as I said, like somebody could just say, go for a run. I do not
stay at home, wash your hands, hashtag COVID-19, then you would annotate it?
As a design choice, we did not do that to make a more conservative system, but definitely you can try to do that.
But it said stay at home, wash your hands, or else you will get COVID-19.
Yeah, then we'll yeah. So
should like just because should it be COVID-19 related or a viral infection related, or if it's something that my friend is feeling nauseous, I think it's the food that she ate last night. Something that is not viral, but if the disease is related, would that be?
So as part of our annotation, the last part is what we consider. So it has nothing to do with the disease at all when we annotate the data. I'll talk about it right in this slide as well. But yeah, I think if by the end of the slide, I think I'll answer your question. Okay. The second thing is where we have a disease mentioned as well, but it has nothing to do with actually stopping the disease. So people are just like, go Corona, or like, I just hate this shit, like, like a lot of public sentiments basically, which has nothing to do with actual events happening, but people are just frustrated with something. So we do not still mark that. But if there's an actual event of happening where we're talking about feeling nauseous, having COVID, those are specific things that we'll mark. So those are actual events which are happening or potentially can happen. And that's what we mark in our annotations. The second thing is, to answer your question, is also about our annotations being disease agnostic. So I have a sentence again, wear masks, that's the only solution for something, where it does not mention anything about the disease, but we have a bias that wearing masks will help prevent COVID, right? And that works well for COVID. So I do not want to still mark wear masks here because it's a very COVID specific preventive measure. If tomorrow there's an epidemic of cholera happening and you have to just drink clean water, wearing masks is not going to solve the problem, and we do not want to give false positives that anyone whenever they mention wear masks, it's a epidemic happening. But if there's a mention about wear masks to protect against COVID, that's a sentence which clearly mentions that you want to protect against a disease and you want to take some action for it. But what I probably want to mark here is the difference of the annotation style itself. We're not going to mark COVID as the term because it's disease specific again. We want to mark as disease agnostic terms as possible as part of our triggers so that we can make the system as a whole disease
So
agnostic.
you don't have COVID as a trigger.
Yes.
COVID is.
It's a role, yeah. So like as part of the role, it is a disease as part of the data set, yeah. So these are just two important principles. We'll come back to this at the end and try to motivate why these principles actually make our system disease agnostic in general. So just jumping more into how the setup looks like. We have a cross-disease setup wherein we train on COVID data. It's not a lot of tweets. It's just like 1,600 tweets that we are looking at. And we tested on monkeypox and Zika dengue data. So this is like cross-disease setup where you only see COVID in your training data set, but you want to generalize to any kind of disease that is happening. And this is a more realistic setup, which we feel we want to focus on. And let's also look at a bunch of models that we try to benchmark. I'm not going to go into details, but this is like a very high level to give motivation of what kind of things people have done and what can people do. So there are these data transfer methods. You have a lot of data sets on event extraction itself. So you can just train your model on different kinds of event extraction data sets, and you can just transfer it to this particular task and setting itself. So ACE and Maven are two general event extraction data sets which exist. You can just train models on them and transfer to this use case. The problem here is the ontology difference itself. They are trained for different ontologies. You're transferring to a different ontology. Next, there are a bunch of zero-shot methods which just use event definitions and external knowledge to solve this task. So if I just tell you infection event is this, identify any kind of infection event from the sentence. And that's what these zero-shot methods do. Third is these no training methods which do not require training. So one is a keyword extractor method, which is just like you provide a bunch of keywords related to certain events, and then you ask the model to extract all of them. And the next is LLMs itself. So like we just provide LLMs with the event definitions, some in context examples, and ask the LLM to identify events from the sentences. And last is the kind of method that we've particularly focused on, which is the supervised methods. We created this speed training data, you train the model on speed, and you test it on the testing data for speed. So let's look at how the results look like. I'm doing this for the two diseases, monkeypox and Zika here as two different columns. This is the performance that our model gives. So like, for monkeypox, you get around 60, 65 F1 score. For Zika, you get around 80 plus F1 score. And this is a supervised model. Now comparing it with the other methods, the data transfer method just failed radically. Because of the ontology difference itself, they do not perform much well at all. The zero-shot method improves, but it's still at a very low range itself. And we also look at keyword and the LLM-based method. So keyword is one of the methods which is typically used by people here. And what you can see is the F1 score is 20 to 25 for keyword-based methods. LLMs show a variance, but it's still like 15 to 35 F1 score. So what we want to highlight here is what's the difference between training a model specifically for this task versus any other method. It's kind of obvious, but from an application standpoint, it serves as an important point about how this supervised training can be very useful in this case.
This is try, right?
This is try. Sorry, I think I messed up on labeling it. Yeah.
Sorry, so you collected speed and trained on it. Where does the data set or test this for monkeypox and Zika?
So we, as part of speed itself, we have the test sets for monkeypox and Zika as well.
Oh, okay.
So we do this curation as well, but we train only on COVID and we test on these.
Is this temporally after the COVID data?
So monkeypox. So COVID data is May 2020. Monkeypox is strictly May 2022 to November 2022, and Zika dengue is actually 2016. So temporarily, they are definitely very far apart. Yeah. Cool. So we see that none of these methods work. Our method shows the strongest performance in general. Now I want to highlight another important aspect. This blue line that you see here is a model which has been trained on it's a supervised model itself, but it's been trained on the target epidemic data, but limited amount of target epidemic data. So just to give a perspective, speed is trained on like 1600 COVID data sets, and the blue model is trained on 300 target epidemic data. So what it means is monkeypox is trained on monkeypox data itself, but 300 samples of them, and same for Zika and dengue. And what we're going to show here is our models are still at par or better than this model, which is trained on the target epidemic data itself. And just taking a 30-second pause here, because this is a very important result from a perspective of early epidemic detection. If you want to build a blue model, you spend a week or more just collecting this data. And in the early stages, the data is very sparse and minimal in nature. So you go through the data, you find these examples, you collect this data and everything. And even after that, your performance is still at par with our model itself. So this shows the utility of the model in these early stages of the epidemic, where you just have limited or minimal amount of data for the new disease, and our model is still able to detect these events.
Can you quickly go to the slide that you had the data annotation?
This one or the one before?
The one before that you had.
Yeah.
So for example, so I'm feeling nauseous again. If it's I'm feeling nauseous, I don't know, maybe I have something, but it's no mention of COVID. So it just besides hashtag COVID, maybe I have something. Would you annotate that or not?
I'll annotate it as a symptom event for sure.
Okay.
For the infection event, we can annotate it. I think the annotators may have annotated, may not have annotated it. It's not a very strict guideline. But for a symptom event, definitely we will annotate that.
And then for that, if there is no mention of COVID, in your basically splitting, you assign it to COVID or one of the others just based on the time of the tweet?
Yes.
Okay.
So,
I think you took the COVID data from May 2020. Is there a reason you didn't take it like March or?
Oh, I mean, we didn't have the data. That was the earliest we had the data for. So yeah, I think that's it. Could, but I feel the system, like, yeah, definitely if you have more data, more quality data, things could change. But even looking at the numbers and the performance right now, it seems like it's at a decent place, even with this data. Yeah.
I'm a little confused about the data selection process for the annotated data. I guess you just meant you were saying, you took COVID data, you took monkeypox data. This is still like in domain in some sense, in that you're already doing some filtering to get it down to COVID. I mean, isn't it really important to test this just on like totally random tweets?
So good question, and I do agree. The problem generally is that we do not have like the data sets that we have either are in domain with respect to the diseases itself, or just general Twitter dumps for the day kind of thing.
But every sentence is a sentence that got annotated, right?
No,
this sentence is monkeypox.
Yeah. We do not do any filtering out there.
So that's the point. Is that like, if it's you're measuring F1, right? So
yes,
it is important.
Yes.
So if you had some kind of like, going to the store today, you annotate that, like that's getting missed, right? So you're
no, I agree. So I think even in the 1600 examples, there are 500 tweets which have no annotations at all in them itself. So they talk about general stuff, So it may not be totally general itself. It might be something related to COVID or not, but it is something which do not mention anything about the event as well.
So that's true in the test set too.
Both in all of them. So when we do this, it's not just that all 286 have events in it. They have some general non-event sentences as well.
I see. Yeah, that makes sense. I just feel like
it can be definitely made better by taking a very uniform sample from Twitter, but I think we just don't have that dump right now with us. So it was just difficult to test it out there. Yeah. Cool. So yeah, just moving ahead in just interest of time here. So this is a result that we saw. We saw that it's doing good. This is all good from an academic setting, but like how does it pan out when you try to do epidemic prediction? So let's Oh, okay. I also have a quick slide about ChatGPT. Just from, again, NLP perspective itself. We give it a bunch of event definitions. We give it a bunch of in-context example for each event itself. We ask it, so COVID, monkeypox, and polio walk into a society. This is an actual tweet which people wrote. And it detects that there's a spread event in the trigger is threats. So there's one hallucination happening. It doesn't know what's happening. And on deeper dive, what we understand is there's a lot of influence of the in-context example itself, and it's just copying something from the in-context example here. So clearly, yeah, there's this gap. LLMs do not do so well in this task here. And yeah, just to intrigue people, I just put a slide here. So going from epidemic prediction to from event extraction to epidemic prediction, what we really do, we collect this tweets from a bunch of data points. It was Twitter, and then the logo changed then. And we pass it through a framework, and we aggregate the number of events that we detect from the data for each of the day. And now we get a continuous time series of what the number of events look like across this time series data. And now what we're looking particularly importantly is the derivative or the delta when we just see a sharp increase based on a threshold. And that's when we will try to give an epidemic warning. Suddenly people are just talking a lot about this epidemic, or this in this time, they're talking a lot about these events. That's the idea. So I think there was one question about trying to apply it to other tasks. So if you just have an event extraction system for a sports kind of thing, you could just do something similar for the sports kind of stuff as well. So yeah, let's look at the results of how it looks like. We do this on monkeypox. It's unseen during COVID. COVID data is 2020, monkeypox is 2022. And this is how the graph looks like. I'm just going to explain this a bit again. So the x-axis is the time of the events happening. The y-axis, the left one, we have the actual number of events detected by the different systems. And the one on the right in the blue dotted line is the actual number of monkeypox cases reported by CDC in the US. What we want to highlight here is we see a lot of these systems doing a spike, a big spike here. That is when WHO declared a global warning, and all of Twitter was just spamming with these things itself. So all of these systems, yeah, we compare it with a bunch of different systems as well, but all of the systems give a spike in this time. But look at the time before that. That's when it's more important, and that's when our system gives these spikes where we see a sudden increase in people talking about it, then it reduces. That's just how social media works. Something gets trending, people talk about it, then they forget it the next day. But we are able to capture them while none of the other systems have any kind of increase in their performance or like doing something like that. Yeah.
What's your measure for issuing the warning? Is it the number of, for example, symptom events detected?
This is just an aggregate right now. So we are not doing it per event. This is just total number of any of these 7 events happening right now.
Oh, okay.
What's the slope threshold?
Oh,
Why not a June warning?
Sorry?
Why not a June warning? You have a bit of a trend there.
Yeah. I don't know exactly, but it should be somewhere in the paper right now. But I can get back to you on that. Yeah.
It'd be interesting to also look at over the same time frame, the same thing, but for H5N1. Because there was no H5, as far as I know. H5N1 thing, so was it also alarmist about that?
True. So this is one of the ongoing works that we're trying to do, where this trend line actually is disease agnostic. There can be just multiple kinds of diseases happening, and you want to be identifying which is a disease of interest and which is not. So we are doing this event argument extraction based thing that we extract the disease and we have trend lines for different diseases simultaneously. But for this work, at least we have it in the disease agnostic fashion. So we.
Oh, so you're saying it's predicting something. It's not necessarily predicting monkeypox.
Yeah, but it's still predicting epidemic events. There are people still talking about infections and spread and a bunch of things, but it could just be about different diseases, and we do not know. Like if, as you said, right, like there could be 5 different diseases infecting people right now. There could just be a seasonal flu. There could just be monkeypox and a bunch of things. You want to be knowing which is the disease so that you can have specific control measures for that particular disease. Currently, because our system is disease agnostic, it just captures any kind of these epidemic events happening. But what I suspect here is still like the data set that we use is monkeypox specific data set itself. So I have looked at the tweets myself too, and 80% of them are just talking about monkeypox in general itself. So the trend line should not change, but a practical use case would be to associate it with the diseases as well. And that's something that we're working on. Yeah. Cool. So yeah, I think that's the main result, that we are able to give these early warnings much before any of the systems can do this, and that's like an important result for us. Another use case of this is trying to do disease kind of profiling. So now we look at the segregation of different events for the disease itself. And what we see is different kinds of profiles for these different diseases. And I'm not going to go into too much detail, but what I want to highlight here is it sort of correlates with the actual properties of the disease itself. So like monkeypox was not as fatal as any of the other diseases, and there are very little mentions about cure and death of monkeypox because people are not worried so much about it. But monkeypox had new ways of transmission, which people were not aware, and there was research going on how monkeypox is getting transmitted. So there are a lot of talks about infection and spread and like these kinds of activities. On the same hand, COVID-19 had exploded by May 2020. So a lot of the talks were just about control measures. How do we control this? How do we get it into control? So as a disease and the time-specific property of the disease, we can do this profiling and it can give us more information about the disease itself. Cool. So towards the, okay, I think I'm pretty much out of time here, but I want to just go back to the designing properties that we had here itself, back to the original thing about like annotating disease agnostic terms versus disease specific terms. And that's the thing that kind of makes a difference. That's the thing that makes it disease agnostic, and probably it's the thing that's more utilitarian for us. That's the part of N1, but I'm pretty much out of time here. So I'm still gonna skip questions for now. I'm gonna quickly rush through topic 2, which I guess will still be of interest for a lot of people here. So it's about multilingual event extraction. So this was a topic again. This will appear in NACL 2024. In general, the problem is event extraction has been developed a lot for English, but not for these other languages. And that leads to poor development of event extraction in other languages. A general way, what people try to do is zero-shot cross-lingual. You just train on English. You want to try to test it on any other language. And these are two generic models which people have built for event extraction itself. But if I actually look at the performance, here I'm trying to compare the supervised and zero-shot performance. Supervised is basically it's being trained on the target language itself. So I have a model which is trained on Chinese data and tested on Chinese data. And I have a zero-shot model which is trained on English data but tested on Chinese data. So we see a bunch of trends. One, there's a difference in the supervised model performance itself. From Arabic to English itself, we see a 10-point difference in the supervised model performance with the same amount of data points. And the second is there's a difference between zero-shot and the supervised model performance itself. And these are the two gaps that we want to fill. And that's the area of improvement that we're looking at. So one of the ways which people do to solve this is translate train. That's been going to be the focus of my work here. What is translate train? You have a bunch of source training data in English. You use a machine translation system and translate it into pseudo target training data, and then you can train a system on the source train and the pseudo target train data. So now you have a sentence in any target language. It has already seen that language in its training data somewhat, and you can get an output on this. So let's say if I do translate train for event extraction, right? This is how an event extraction example looks like. So you have a sentence. You have the trigger, you have place, and they're annotated with the spans. So like it's the exact tokens in the actual sentence to which it corresponds to. If I do machine translation, I can translate it to Chinese here, which is my target language. But it is a difficult way of how to translate a trigger and place because you do not know the spans of the trigger and the place in this actual translated Chinese sentence. So that's the problem, and that's the problem which people term as label projection. So you want to project the labels into the target space. So just a quick technical definition of what this looks like. I'm using X and Y as the input and output, which is X is the sentence, Y is the labels in the sentence, and source and target indicate the source in the target language. So the problem of label projection is to jointly translate the sentence and the labels from the source language into the target language, such that the labels, the translated labels, which is Y target M, is present in the translated sentence, the X target. So that's a constraint that we wanted to satisfy. So the first two properties are kind of measuring the accuracy, how accurate your data is. If the translation quality is good, your data is more accurate in nature. But the last property kind of dictates the usability of the data. If your target label is not present in the target sentence, then you cannot use it for event extraction at a data point. So again, let's take an example. Coming back to this, in Florida, we had this example, we had a bunch of arguments. A label projection system should be able to translate it with having the exact spans of the sentence in this Chinese sentence. And again, the quality of the translations indicates the accuracy of the system. And since these words are present in the actual sentence, this indicates that the system is faithful in nature. So that's just a quick brief background about the problem statement that we are working on. I want to quickly introduce some simple methods which people do to solve this problem. So one is like a word alignment. You have two sentences which are translated pairs of each other. We use an external tool to align the tokens and the words across these sentences. So you exactly know that this token corresponds to this particular token in the target sentence. And now you can get the spans of the target sentence from this, and that can solve your label projection problem. But again, word alignment systems are not perfect. There are morphological differences between the sentences, and that leads to error propagation. So this is not a very reliable method in general. Another method is trying to hack the system, which is like the marker-based translation. What you do is you have the original sentence, you add specific markers to the sentence and as a pre-processing step, and then you translate the sentence. So what happens is many times these markers will be retained as is even in the translated sentence. And now you exactly know that the word between this marker corresponds to the word between these markers across the two sentences. So it's kind of hacking the system that machine translation systems are good at retaining markers, and you can use that to actually project the labels. But again, the problem here is you're relying too much on machine translation system. If the markers are not retained, then this is lost. And the second thing is, when you add markers and translate the sentence, the translation quality drops. You don't get the exact best translation as you would want it to be. So these are the flaws of the previous works, and what we introduce here is CLAP, which is our work. Mainly, we have two steps. One is translation, which is just the basic translation of the input sentence to the target language itself. But the second is a contextual machine translation step. So wherein what we want to achieve is we want to translate Y source M, but conditional on the X target. So we know that the input sentence has been translated, and conditional on that, we want to translate this particular token. So this is what we would possibly want to achieve, that using this as a conditional input and this as the actual translated input, we want to have the translated output to be one of these. Now we can think of a bunch of ways to do this. So like a simple way would be just doing independent translation, right? I remove the conditional part, I just do an independent translation and translate it. But suits can have a lot of translations. Suit can mean lawsuits. Suits can mean the suits that you wear as a garment. Suits can also mean a verb. So there's this word disambiguation problem, and your translated word will not exist in the translated sentence itself. So that's a problem. And these systems can have high accuracy, but they'll have low faithfulness in general. Another way that we tried is doing constraint translation, wherein we add like a decoding time constraint that when you have, like, you can just use tokens from this particular sentence when translating the sentence itself. So this is like an NLP way of doing a decoding time constraint, decoding kind of setup. But the problem here is it affects the translation quality significantly. And the words that you get are typically a little bit meaningless, and it generally leads to low accuracy but high faithfulness. So those are the two extremes of what we can do. What we try to do instead is trying to use instruction-tuned language models here. And we kind of encode the faithfulness constraint as part of the instruction for this instruction-tuned language models. So just a quick brief example, we have the input sentence, we translated it to the output space, which is X target here. And now we make kind of a prompt that we say that this is a Chinese sentence which has been translated. Now I say for the previous sentence, the words corresponding to Florida is, and we prompt the model to ask and answer this question. So now the model understands that it has to find the word corresponding to Florida from this particular sentence here. And we give it a couple of in-context examples, two in our case here, and that makes our system for doing contextual machine translation. So once we look at the output, we get the exact words corresponding to Florida and suits as the output of the system. As a technical thing, we use Llama 2 13B for doing this thing. And why I want to highlight this is because primarily it's just monolingually we train on English itself. 98% of the data for Llama 2 13B has been English itself. So it's not a very strong multilingual model. And multilingual generation of this model is also pretty bad, but it's able to understand multilingual text pretty well. And that's why it works well for us. Our experimental setup, we try it on NER and event argument extraction as 2 tasks. We do it on 39 languages for NER and 2 languages for EAE. We have these baselines, the ones which I talked about, the word alignment based and the marker based baselines. And we do 2 kinds of evaluation. Intrinsic evaluation is measuring the data quality, how good is the accuracy and how good is the faithfulness of the model. And extrinsic evaluation is we take this data, which is translated by the model, train a downstream model on it, and now we test the actual performance of the downstream task in these different languages. And here's how the performance looks like. Again, intrinsic evaluation is accuracy and faithfulness. A quick go through is accuracy is just measuring the translation quality of X target and X source, Y target and Y source. Faithfulness is how much times Y target is present in X target. And in this graph, we show the 3 methods by the 3 different colors, and we show the 2 tasks by 2 different shapes. So first, what I want to highlight is if I just look at accuracy, our method is much better in accuracy compared to any of the 2 previous methods. So what we want to boast about is we improve the accuracy significantly for both the tasks in general. Second is if I just look at EAE, which are all the square pieces here, we are best in accuracy and best in faithfulness as well. So like the better the model, the better it is to the top right of this graph in general. So if I just compare these 3 points, we are better in faithfulness and better in accuracy for event argument extraction. When I look at NER, there's a drop in faithfulness, but there's a boost in accuracy at a larger scale. So this kind of indicates the kind of data quality of our model and how well it's doing. And I'll also take a look on the extrinsic evaluation. So again, this is averaged over all the languages together itself. What we see is our model performs better than any of these other methods and improves across the scope for both the tasks in general. The other thing I still want to highlight here is this baseline, which is the orange color, which is the LLM input. What we are doing here is we just prompt the LLM to do event extraction directly in the target language. And the performance is pretty bad. And the takeaway here is if you're just using LLM to do an inference, it's not a good way to use LLMs for multilingual tasks in general. But the way we were using LLMs, we were able to show a massive improvement compared to the other methods. And that's a better way to do it. In general, as a paradigm, it's better to use LLMs for data generation perspectives than doing extraction directly. And yeah, I'm just going to skip this ablation slide for a bit right now. But yeah, this is another thing I wanted to show. We also tried on extremely low resource languages. So these are languages from Africa and South America, for which the data has been very sparse in general. I'm not sure myself if Llama 2 was actually trained on them or not. But the idea being Llama 2 still understands the languages more specifically. We do not show out of the chart improvement on this. We show improvements over a 0 shot for 6 out of 10 languages. We are the best on 3 out of these 10 languages. But the idea being that even a monolingually trained small LLM model, instruction tuned model is able to give performance on this at a.
When you say extremely low resource, what do you mean? I mean, can you give some examples? How low?
So like we look at
just give a few examples maybe.
Yeah, I don't actually have the numbers, but why we call this extremely low is the papers that pitched this languages and created data sets for these languages would talk about it in this way. What I can still say is the resources in terms of NER data, which is one of the more easier tasks to annotate, would be around 1,000 to 10,000 samples. And that's the scale of all of these languages currently here.
So it's like Zulu and Kosa.
Yeah. So
Quechua.
Yeah. So 9 of them are from Africa. Quechua is South American. Here, yeah. Cool.
little bit confused on the intuition about why Llama would perform well at all, given that it hasn't been trained on those languages at all. Like,
True. So my understanding, what I got from this project genuinely was LLMs are not so great at multilingual generation as you go from medium to low resource languages itself. For high resource languages, it's still pretty decent. But it's good at understanding languages. If I like the way we have the prompt, right? We say that this is a sentence. Yeah, this is a sentence and identify the word corresponding to this from the sentence. So if it understands what this word is and it has a basic understanding of what this sentence means, it does not need to know everything in the sentence, but it just needs to identify what specific segment of this sentence corresponds to this particular word. So it's an easier task, I feel, the way we formulate it. That's my intuition about it. Yeah.
So it was low resource stuff just for NER?
Just for NER.
So, and these are all Latin script languages, right?
I guess so. Yes.
So I guess it would be interesting to know.
Yeah.
Degree the named entities were.
Yeah.
Let's say cognates to be generous.
Yeah. No. I don't understand the languages, but I looked at a few examples, and I think there is this basic thing that it is many times very similar or some morphological inflected word of the original sentence. Like there are a lot of proper nouns in this as their named entities, but there are certain words as well, like the Federation of Football Association, which might be written in different ways. But it's
you'll also get colonial.
Yeah.
So it might not be English, but it might be French.
It could be. Yes. But I do agree. NER is definitely a much easier task in this respect, and the gains might be inflated because of that. But like from an experimental standpoint, that's the best we were able to get in terms of tasks and the data for these low resource languages. And in general, what we wanted to show is it shows potential, and you can potentially apply it for more tasks and more low resource languages going ahead.
Also, if there are many cognates, you would expect single shot.
Yeah. Well, sure.
It's
the advantage of class is that you're constraining. Softly constraining. The content.
Yeah. So I think just going back to the slide where we showed the difference, this is where CLAP stands. We do not completely solve the problem, and then there's definitely so much we can do, but we still reduce the gap, and that's that gap. The remaining gap is still something that we can work towards. So I think that's the end of sort of my presentation. We talked about multilingual event extraction, and one of the future works that we are trying to do is integrating CLAP with speed and trying to build this multilingual global scale epidemic prediction framework itself. And something we also want to step into is like trying to do this misinformation, fake epidemic news detection thing. So like we can capture a lot of news that do this to prevent COVID, and like, how much of that can be true or not. This can also be useful information for public policy officers to worry about. So and that's the end. That's just a thanks to my team, my advisors, a couple of my senior PhDs, and my undergrad team as well. So thank you for the talk.
Awesome. I know we're timed, but do we have any quick questions? Okay, cool.
The last thing is that you wanted to apply this to misinformation detection.
Yeah.
Can you give me a 1-sentence explanation about how you might do anything?
I don't. So not exactly misinformation, but at least a knowledge aggregation perspective. So when we apply it on millions of tweets, we can aggregate information of what are the high set of preventive measures that people are talking about to prevent COVID. We are not going to take the call that this is right, this is wrong, but instead of a public health officer going through millions of tweets, we can just give it like these are the 15 top methods that we can apply, and that's where we want to have its application for.
I would like to, as a former journalist, quibble with a small point that you made early on, where you said, Twitter is always going to be faster. Because that's actually, period of point of great debate. And like there was a period of time in journalism where people were like, oh yeah, let's use Twitter for news detection. And it was just very mixed. Like most of the time when we saw events emerging on Twitter, they had their, causes were external news articles that then got like retweeted and paired up and like reframed around. So I guess that leads me to my question. When you're extracting events and finding predictors and finding these spikes or whatever, do you have a sense of how many are kind of true organic users versus news articles, other people like, you know, just tweeting about what they heard in other sources of stuff?
So, good point. And I am not the best person to answer about journalism and social media. My statement mainly came from a couple of previous works which talked about how infectious events, at least people mentioned, start talking about it earlier on social media data than news. But this was again still 15 years outdated. So I'm not gonna claim much on it. The other thing about organic users versus actually people just talking about the same thing. One thing is we removed all kinds of retweets when we have the spikes. So this is not about people retweeting the same thing, but it's also about people maybe paraphrasing and tweeting about it. That is something we can't help, but at least the retweets are definitely out. So a good portion of the tweets, which if it's a news article and people are retweeting, might not be considered here. But I have not done a qualitative study on looking at the tweets itself, and I wouldn't have the best of answers there. Yeah. But I do agree. It goes hand in hand, news and social media. And I did personally see that a lot of times people do talk about news articles or somebody claiming something happened and they're just talking about the same thing again. But a lot of time people also talk about personal stuff which we are capturing here, which potentially news might not be able to capture directly. Yeah.
Awesome. Let's thank Tanmay once again for a very insightful, important implication. So thank you so much for that. And I think we ended on a strong note for the ISI NL seminar this semester. So that was the last one for this semester, and stay tuned for when we're back in the fall semester.
There might be some summer one-offs.
There might be some summer one-offs depending on bonus episodes. But yeah, all right. Thank you so much.
Thank you.